All right, telemetry systems are green. Welcome, flight crew, to this explainer. I am your flight director, and if you are currently running pre-flight checks for Cambridge Mathematics AS and A-Level, specifically syllabus 9709, well, you have docked at the exact right station. Today, we are treating your exam paper like a highly complex flight system that requires absolutely perfect execution. Our primary mission objective: breaking down a foundational pillar of calculus: integration. Specifically, we're looking at it as the reverse of differentiation and zooming in on how to apply it to that famously tricky expression, ax plus b all to the power of n. You are going to see this in literally every single examination series. Master this procedural framework, and it becomes a reinforced fail-safe vault for securing your marks. Now, on the central console today, I'm tracking two theoretical candidates in our simulation. We've got pilot Alex, who tends to overcomplicate data calculations and burns way too much time and mental fuel, and pilot Sam, who often ignores structural boundary constraints and risks total systemic breakdown. Our goal is to make sure you fly a perfect path right down the middle. Okay, let's dive into this, because this right here is the multi-million-dollar question. It's the biggest anomaly in our pre-launch telemetry. Year after year, candidates understand the basic calculus. They know the theory, but when they actually sit down in the exam hall to execute multi-step area calculations or find equations of curves, they start bleeding marks rapidly. Why does this happen? Well, it's because students often treat integration as just some isolated mechanical operation. Pilot Sam, for example, rushes the algebra without checking the flight conditions. Pilot Alex gets bogged down expanding brackets instead of using the rules. Both fail to follow the strict analytical framework that Cambridge examiners are actually testing. To fix that trajectory, we are going to use the ultimate examiner's playbook. We've got a 4-stage flight plan for this explainer. First, core principles. Second, the procedural framework. Third, critical analysis. And fourth, the top examiner warnings. Let's lock it in. Initiating sequence 1. Let's look at section 1, core integration principles, and the foundations of ax plus b to the power of n. Cambridge candidates absolutely must demonstrate complete mastery of these fundamental mechanics before attempting complex maneuvers. At its core, the syllabus strictly defines integration as the direct, undeniable reverse of differentiation. Think of it as putting the engine into reverse to trace your exact trajectory back to the launch pad. When we apply this to the expression ax plus b, wrapped in parentheses and raised to the power of n, it requires a very specific sequence. It means not just adding 1 to the power and dividing by that new power, which is where pilot Sam usually stops, but crucially, you absolutely must divide by a. And what is a? It's the derivative of that inner bracket. Cambridge isn't just testing rote memory here. They want to see connected, conceptual understanding. You have to be able to transfer this principle to entirely unfamiliar functions when the exam inevitably throws a curveball into your flight path. Now, what's really interesting about this slide is how it breaks down the exact system parameters you need to clear orbit. The assessment framework systematically targets 3 distinct cognitive domains. First up, knowledge and understanding. This is your mastery of the absolute fundamentals, like definitely not forgetting your plus c constant of integration. Seriously, don't leave the launch pad without your constant. Second is application. This is taking that ax plus b formula and transferring it to find, say, the exact area under an entirely unfamiliar curve. And third, analysis. The exam explicitly prioritizes analytical depth over superficial breadth. They want to see the clear logic in your algebraic manipulation on the page, not just some guessed final destination. Let's shift gears and move into section 2, the procedural framework and technical methodology. This is the part of the simulation where you develop truly professional mathematical skills. Let's move to the high-tech UI console overlay and see how this builds into a practical methodology for problem solving. But hold on, pause the simulation. Before we fire the secondary boosters to secure maximum marks and totally optimize your flight path, I need you to do something critical. Subscribe to Ace the Exams at Ace the Exams right now and turn on all notifications. Okay, boosters engaged, let's resume. When facing a highly complex past paper problem, you need a systematic approach. First, identify given information. Isolate your boundary limits or coordinate points. Second, break it into logical steps. Third, solve systematically using your rules. Fourth, evaluate for reasonableness. If you hit a critical roadblock mid-paragraph where your mathematical evidence fails, you need a structural template. Think of it like a peel structure. Point, evidence, evaluation, link. What's the point of the calculation? What's the mathematical evidence? Evaluate if an area strictly above the x-axis is showing up as positive. And finally, link it back to make your justified recommendation or final value. While executing those precise maneuvers, you must adhere to strict presentation conventions. We're talking proper headings, correct mathematical terminology, appropriate formats, and crystal clear annotation. You have to keep your integral signs and your dx terms perfectly organized, right up until the exact moment the integration actually happens. Listen to me on this. Formatting isn't just about making it look pretty. Following these strict conventions is a required, professional system diagnostic skill for securing marks. Scattered, messy algebra is just debris in your flight path, and it leaves easy points sitting right there on the table. Entering the upper atmosphere now with Section 3, Critical Analysis and Evaluation. This is the highest cognitive tier of the exam, where logical, structured reasoning is absolutely paramount. All right, crew, this is where we initiate our interactive viewer radar challenge. I want you to imagine a 60-second visual countdown clock ticking away on your screen. You're looking at a highly complex source graph. To evaluate the evidence quality, you have to find the hidden core variable. You must look beyond the raw numbers. In calculus, critical analysis often means identifying mathematical limitations. Did you check your assumptions? For instance, realizing you absolutely cannot integrate across an asymptote. Did you catch that boundary condition before the clock ran out? Are you calculating an area that suddenly dips below the x-axis? If so, you have to split that integral so the positive and negative areas don't cancel each other out and destroy your conclusion. This systematic graphical analysis is exactly what examiners are hunting for on your radar. And this brilliantly illustrates our second simulation, debris detection. When a question asks you to perform a comparative analysis, like evaluating the area of two distinct regions, you have to explicitly identify the mathematical relationship between them. If one calculated area has to be subtracted from a larger rectangle to find a specific shaded region, your structural reasoning must be screamingly obvious on the page. We need to detect the debris where student answers fall below compliance. You cannot just list two numbers side by side and hope the examiner figures it out. You must actively contrast both sides using specific comparative connectives to draw your relative conclusions. All right, final descent sequence initiated. We are moving into Section 4, Top Examiner Warnings. This is the insider's view, pulling data directly from the Cambridge Principal Examiner reports. So, the crucial point is right here in the black box data. The examiners are incredibly clear on one major system failure. Students lose marks by not showing their working. Even if your final answer is completely wrong, method marks can save your trajectory. This is the ultimate method mark strategy. Your systematic working out is honestly often more vital than a flawless final touchdown. Let's say pilot Alex makes a tiny arithmetic error early on, but then executes the incredibly complex ax+b integration perfectly based on that flawed number. Method marks will literally rescue the grade. Never ever skip showing your steps. Let's run through the top 3 system failures examiners continually report so you know exactly what traps to avoid. Number 1, confusing cause and effect. Basically, mixing up the rules of integration with differentiation. This happens all the time when students multiply by the derivative of the bracket instead of dividing by it. Big mistake. Number 2, forgetting to check format and presentation. Sloppy pilots lose easy marks because their upper and lower limits aren't substituted clearly on the page. And number 3, context. If the problem asks for a physical volume of revolution, leaving your final answer as a negative fraction makes literally zero physical sense. It implies a total systemic breakdown and will cost you crucial points. To make sure you don't fall into these traps under the massive pressure of a ticking exam clock, you need a failsafe. Build a mental checklist. Create a memory hack for the ax+b to the power of n rule. I like to use add, divide, divide. Add 1 to the power, divide by the new power, and divide by the inside derivative. Lock this structured reasoning into their brain right now. When you flip over that exam paper, I want your pre-flight question scan checklist kicking in on absolute autopilot. Mission accomplished, crew. Both Pilot Alex and Pilot Sam have confirmed a successful full-mark touchdown sequence by following the parameters. We've mapped out the core principles, the strict formatting requirements, and the exact errors examiners are tired of seeing. But listen, this telemetry is only useful if you actually apply it. So I leave you with this final critical thought. Will you apply the method mark strategy and explicitly write out every single integration step on your very next past paper? Do not wait for the real exam to test this flight path. Start practicing this methodology today. Before you log off, do your final post-flight check. Subscribe to Ace the Exams at Ace the Exams, enable that notification bell, and drop a comment below sharing your specific subject and tier. Thanks for running this explainer simulation with me. Keep practicing and keep your trajectory aimed high.